For directed graph, we have a similar set of notation. Okay. So let's say this is U, let's say this is V, and let's say this is E. So this time this is a directed graph. In directed graph, we are saying U is the initial vertex of E, and then V is the terminal vertex Okay, so here we are going to, we're not just calling them endpoints, so they are still endpoints, but then they are having different role. So for a particular edge E, so this is the starting point of E, and this is the ending point of E. So this is called the initial vertex, and this is called the terminal vertex. Is that okay? And then what? And then, so we are saying that U is adjacent to V. So this is a 2. So it is like U to V is an edge. And then we are saying that V is adjacent from U. So this is from U. So we are saying that U is adjacent to V and V is adjacent from U. So from U. Okay, so this is U from U. It looks like this. So we are still talking about the same thing. So there is an edge that joins from U to V. Is that okay? And then the same, if U and V are the same, so this is still called a self loop. This is called a loop or a self loop. Now, for a directed graph, when we talk about degree, we differentiate the degree as two different types. We are going to talk about in degree, and we are going to talk about out degree. Okay, in degree is the number of edge entering. So there is a loop here. So let's make it more specific. It is a directed graph, right? So in that case, let's say the loop, it needs to have an arrow. Okay. Okay. In degree is the number of edge coming into a node. Out degree is the number of edge going away from the node. Okay. So if we are looking at this node, what is the in degree and what is the out degree? So in degree is equal to what? Just 1, am I correct? One edge coming into it, and out degree is 1 as well. So in is 1, out is 1. How about this one? This one, the in degree is how many? The in degree is 1 and 2. Is that okay? And the out degree is equal to 1. And for this one, the in degree is 1. Is that okay? And then the out degree is 0. Is that okay? Is that okay? And this one also in degree 1, out degree 0. This one in is 1, out is also 1. This one in is 1, out is 0. Is that okay? Now this is special. This is, we have a loop. Is that okay? We are counting how many in. So in is just 1 in. This is 1 in. In is here is equal to 1. Is that okay? How many out? This one is out, this one is out, this one is out, this one is out. So out degree is equal to 4. Okay, if you understand the concept of degree and also in and out degree, could you please raise your hand? Good, excellent. Now, this is the next one is a very easy lemma, but it is useful. Okay. The next lemma is called Handshaking Lemma. Okay. The Handshaking Lemma says, in an undirected graph, total degree, the sum of degree of all vertices must be even. Okay, so this is the Handshaking Lemma. If you sum up the degree of every vertices, so here it is 1 plus 3 plus 3 plus 4 plus 1 plus, sorry, this is not 1. This is what? I forget. This is 3. Okay. 1, 3, 3, 4, 3. Okay. If I add all the numbers here up, it has to be even. It has to be even. Why? Why? No matter what happens, it has to be even. You can think about proving this by induction, but there is an even easier way. This one is 3. It is like 1, 2, 3. Am I correct? This one is 3. It is because it is 1, 2, 3. This one is 1. It is 1. This one is 1, 2, 3. This one is 4. It is 1, 2, 3, 4. Is that okay? Now, if you look at each edge, if you look at this edge is counted 2 times. One is when it is counting 3, 1, 2, 3. This is the first time that this edge is used in the summation. And then this edge is also counted when you are counting 1, 2, 3 here. If we are going to sum up all the degrees, each edge is counted twice. Is that okay? Each edge is counted twice. So actually, the summation of degree is just, it is not just even. It must be equal to 2 times the number of edges that we have. Okay? Because each edge is counted twice. So for instance, in this graph, how many edges are there? 1, 2, 3, 4, 5, 6, 7. There are 7 edges. 7 edges. And then it is equal to 4 plus 3 plus 3 plus 3 plus 1. So this is the summation of degree. You divide it by 2, it turns out that it is equal to the number of edges. Is that okay? Or the summation of degree is equal to 2 times the number of edges. Okay, this is always true. Simple, right? Yeah, this is the Handshaking Lemma for undirected graph. Now, we have a similar lemma. Let's call it the directed version. In a directed graph, the sum of in degree of all vertices must be equal to the sum of out degree of all vertices. So in the directed version, the sum of in must be equal to the sum of out. Let's take a look at this case. Sum of in, let's count it. 1, 2, 3, 4, 5, 6, 7, 8. So sum of in is equal to 8. And sum of out, 1, 2, 3, 4, 5, 6. Once again. Did I make a mistake? Let's count it. 1, 2, 3, 4, 5, 6, 7, 8. Yes? How come? How many edges are there? There is 1, 2, 3, 4, 5, 6, 7, 8. There should be 8. What's wrong? Out is 1, 2. V? Oh, thank you. Okay. Thanks a lot. Yeah, otherwise, I cannot debug it myself. Okay, debugging. So, sum of in 1, 2, 3, 4, 5, 6, 7, 8. Thanks. And sum of out 1, 2, 3, 4, 5, 6, 7, 8. Okay? Why? Why is the sum of in is equal to the sum of out? It is because each edge will give you one in and one out. It is giving one in to the terminal vertex, and it is giving one out for the initial vertex, right? So it is not just the same, it is equal to the size of E. Okay? Is that okay? So these are something that I want you to know today, okay? And then, okay, and then before the exam, so, okay, so what it remains is not important, okay? But it is about the last exam. So in the discussion board, someone asked this question. So this is one of the assignment question. So among 10 people, so this is the pigeonhole principle problem. So among 10 people, between every pair of them, they have to be either friends or enemies. We want to show that there must either be 4 friends, 4 mutual friends, or 3 mutual enemies must exist. Must exist. Okay, so this is part 1. Part 2 is stronger. Part 2 says, okay, you don't need 10 people, you just need 9 people. Okay. Let's do part A first. Okay. 10 people. How do we show? How do we show? So we start with 10 people. We need to recall a theorem, okay? When there are 6 people, it must have what? 3 mutual friends or few mutual enemies. This is what we have done in the class. So I'm not going to prove this again, but we have known this already. Either there is 3 mutual friends, or there are 3 mutual enemies, or both. Okay, now we have 10 people. So you can pick up 1 people, and then there are 1, 2, 3, 4, 5, 6, 7, 8, 9. There are 9 people around it. Okay, so we are going to show this is always true. So how do we show? Okay, so there are 2 cases. Case 1. Case 1 is for this one, it has 6 friends. So if this one has 6 friends, what will happen? Okay, so maybe this one, 1, 2, 3, 4, 5, 6. Let's say these 6 are friends with this one. Okay. Now, if in this case, 6 friends. Okay. Now, among these 6 people, we know that there are either 3 mutual friends or 3 mutual enemies. If there are 3 mutual friends, let's say this one is friend to this one is friend to this one is friend to this one, then what will happen? We will have 4 mutual friends. Is that okay? Is that okay? But on the other hand, if we do not find any 3 mutual friends in this group, there will be 3 mutual enemies. Is that okay? Yeah, because these are 6 people. Among 6 people, there are either 3 mutual friends or 3 mutual enemies. Either there are 3 mutual friends, then in that case we have 4 mutual friends for the whole 10 people. Or there are no 3 mutual friends, then in that case there are 3 mutual enemies. So case 1 is okay. If you are okay with what I'm telling so far, could you please raise your hand? Okay, excellent. So if there are no, okay, now this is 6 friends. So we can add a condition, at least 6 friends. So, right? When you have at least 6 friends, you have 6 friends. I just pick up these 6 to take a look. So if this is case 1, this is about case 1. And case 1 is okay. Now how about case 2? Case 2 is this person does not have at least 6 friends. What happened? So it does not have at least 6 friends, so it must have at least 4 enemies. Am I correct? Does that make sense? Because there are 9 people already here. There are just 9 people. If you don't find 6 friends, so there are at most 5 friends. If there are at most 5 friends, then there are at least 4 enemies. Is that okay? Is that okay? So let's say this one is an enemy, this one is an enemy, this one is an enemy, and this one is an enemy. Is that okay? Is that okay? Now, if any one of them is enemy to each other, if let's say these 2 is an enemy, then we get 3 mutual enemies. Okay? In order not to get 3 mutual enemies, these 2 has to be friend. 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 And these 2 has to be friend. Is that okay? If any one of them is not friend, then we get 3 mutual enemies. Is that okay? So it forces us up, if we don't find any 3 mutual enemies in case 2, we must have 4 mutual friends. So this is also okay. Is that okay? So when we have 10 people, we must always have 4 mutual friends or 3 mutual enemies. If you understand what I'm talking about so far, could you please raise your hand? Good, excellent. Now, let's change this problem to, let's say we have just 9 people. Now when we have 9 people, the story changes a lot, okay? Because it is not like case 1 and case 2. If you have at least 6 friends, it will be okay. If you have at least 4 enemies, you will be okay. But it may be a case that you don't have at least 6 friends or you don't have at least 4 enemies. What is that case? So if there are just 9 people, so if we pick out 1 here, 1, 2, there will be 8 people left. 1, 2, 3, 4, 5, 6, 7, 8. Is that okay? Now, when this one has 6 friends, okay. When this one has 4 enemies, okay. But we are not getting lucky every day, right? Maybe we are still having a third case, case 0 or case 3. So there is a problematic case. Case 3 is, so this is at least 6 friends, at least 4 enemies, right? So what is the remaining case that we need to consider? What is that? What is that? You are at least 4. So okay. So here again, we can apply the same rule as before. If there are 6 friends, okay, we get 3 mutual friends or 4 mutual friends or 3 mutual enemies. If there's 4 enemies, it's okay. But there is still one thing left. It is not always have 6 friends or 4 enemies, right? What will happen if we do not have 6 friends and we do not have 4 enemies? What does that mean? Yes, yes? It's very good, excellent. So there is a case 3. This is the problematic one. We have 5 friends. And then we have 3 enemies, right? Enemies. So this is a case 3. We have 5 friends and 3 enemies. In that case, we cannot duplicate our argument. Is that okay? Okay, now, if we cannot duplicate our argument, then what shall we do? So we are not that stubborn, okay? So if this one has what? This one has 5 friends and 3 enemies, then this is not a good case for us. So we don't use this. We pick up another one. Maybe this one, we get lucky. Maybe this one has 6 friends, or maybe this one has 4 enemies. Then in that case, we are lucky. Then we can go again with the same proof. Do you understand my point? But we may be very unlucky, right? We may be unlucky, and then we have 5 friends here, and then 3 enemies here. Is that okay? Then in that case, what will happen? Then we pick another one. But then we may be unlucky, 5 friends, 3 enemies. Okay? Okay, but can we always get unlucky? I'm going to tell you that we cannot. Okay? We will get a contradiction. So it is not what I'm claiming is that it is not possible that every one of them is 5 friends and 3 enemies. It cannot be. It cannot be. The reason is that, so can it be, so problematic case is this one. So this is my question, can all people can everyone have exactly 5 friends and 3 enemies? Can everyone have exactly 5 friends and 3 enemies? No, it can't. It can't. If it is really the case, then you draw a graph for me. This graph will have white edges. Let's look at the white edges. How many white edges are there? So the total number of white edges must be equal to the total number of white degree, adding up together and then divided by 2. Am I correct? This is the handshaking lemma. We focus on only the white edges. We forget about the green edges. Is that okay? Okay. The total number of white edges must be equal to the number of white edges for this one, plus the number of white edges for this one, plus this one, plus this one, plus you add up all of them, and then divide it by 2. Am I correct? Is that okay? How many people are there? 9 altogether. And if everyone has exactly 5 white edges, then the total degree of white edges will be 45. And then the number of white edges is going to be 22.5. It can't happen. An edge is an edge. It is not half an edge. Is that okay? So you will get a contradiction. The contradiction says you cannot have all the people having exactly 5 friends and 3 enemies. Because in that case, the number of friendship relation will not be a whole number. Will be 22.5. It is impossible. So you either have 1 white edge, 2 white edges, 3 white edges. You cannot have 4.5 white edges. Is that okay? So in that case, for the case of 9 people, either you are lucky to get case 1 or case 2 immediately for picking up the first vertex. If not, you pick the second one. If not, you pick the third one. But it is guaranteed that in this process, at least one of the vertices will have case 1 or case 2 happen. It cannot have all the vertices having case 3. It is impossible. Okay, and how to prove this? This is by the handshaking lemma, or similar flavor of the handshaking lemma. Is that okay? Good. Okay, excellent. Okay, so let's be lazy today. Okay, so let's end the class now, and then we will continue the discussion on graphs on Wednesday. Okay, thank you.